This is the first lesson for Unit 4 for AP Calculus. This is the unit where we're going to look at how you can apply all the information you know about derivatives to various problems. And right off the start, we're going to be doing about 4 lessons, just looking at how you can use derivatives to help you draw a graph or interpret a graph. And off the very start, we're just going to take a look at interval notation and see how that relates to various sections of the number line. We're going to need to describe different sections of the number line as we go through, especially the first third of this unit. And the first one here, we've got this set description that says x is chosen such that it's squeezed in between a and b, but not equal to a and b. And if I was to just draw that on my number line, I would put open circles here saying, hey, I can't be a and I can't be b, but all of these numbers in between, those are fair game. Now, it's great to draw that picture and it's great to have that set notation, but we need a short way to write this. And here's how you can do that. You can use round brackets and just say, yep, I know that looks like a point, but it's really not. It's actually an interval of x values, and it says it's going to go from a to b and not including a and b. The very next one, we can deal with how do you show it that it might be okay for it to be a and b. Like what if it's greater than or equal to a and less than or equal to b, right? And you have these filled in circles there like that. And what we do for interval notation is we just use square brackets. So square brackets include those endpoints. And you can mix and match. So here's a couple where we can mix and match. This one says, well, a is fine, but b is not. And then also all the numbers in between a and b are great too. That's in contrast to the next one that says a is not, but b is okay. And all the numbers in between are fantastic. And so we can draw that in interval notation really nicely. This one here, we can say include the a, we'll use a square bracket, and then don't include the b, we'll just use a round bracket there. Or the other way around for this one, right? Don't include the a, round bracket, and include the b, right, with that closed end. Sometimes we want to talk about the numbers that just go from one value up. So this is all the numbers bigger than a. Okay, so that would look like this, and you would basically just say, yeah, that just keeps on going. Here, I'll put a little arrow on that. Yeah, don't worry about b. We're going to go right on past that. For interval notation for that, we're going to say, well, it starts at a, or maybe I should say it starts right after a, so we'll use a round bracket. And then we want to go to forever, and so we can just draw that with the notion of infinity. But for historical reasons, we don't put square brackets on infinity, probably because it's not really a number, it's more of a notion. And infinities are always going to be nice round brackets. You might include the a, so maybe it's like this, like a is good, and then every number larger than that is fine. Then you can go square bracket on the a, but we would still go round bracket on the infinity. The next one, what about going backwards? Yeah, we could say from a down, but not including the a. That would look like that. And then the one right underneath it is going to be basically the same thing, but we'll fill it in and say, yeah, a is fine, and anything below it, kind of going that way. So the interval notation there would say, oh yeah, we're going to go from minus infinity with that round bracket. Sometimes I call those soft edges, and all the way up to a, and again, soft edge on that one. This one says, oh yeah, we're going to go from minus infinity all the way up to a, but a is okay. So I sometimes call that a hard edge, right? But we'll put the square brackets on that. And sometimes the entire number line is fine, like the whole deal. The domain of a function might be like all reals, right? Just the whole thing is perfect. So we can denote that quickly in interval notation like this, negative infinity to infinity, and always round brackets on the infinity. Looking back up near the top, the very first one, that one that has the round brackets and round brackets, the open interval, that's what it's called. Let's just put that in our notes here, okay, with those soft edges. And if it does include the endpoints, we're going to call that a closed interval because it's nicely closed on the ends. There's some very clear endpoints for the beginning and for the end. All right, with that knowledge in hand for how we can quickly talk about intervals, let's dive into this, and we're going to take a look at how you can find really large or really small y values, what we would call extreme values. And looking at this little box over here on the left, it's talking about local maximums, and another name for that, interchangeable name of that, you'll also see people talk about relative maximums. Completely interchangeable words. Okay, there is a lot of technical talk here. A function f of x has a local maximum value of f of c is capital M at x equals c if f of c is greater than or equal to f of x for all x near, like, whoa, that is a lot of stuff. Let's decipher this and figure out, like, what is it trying to say? Well, there's some sort of x value. Let's just put that maybe right here. And we'll say, okay, that is going to be some special x value that we're going to call c. And this graph is going to hit some maximum right here. So this is going to be my largest y value in that area, in that neighborhood, we would say. So let's go and put a point right here. All this is saying, if you take a look, is that the actual f of c, which is this capital M, right there. So this is f of c. It's saying that is as big as the function gets, right? The function will equal it there, and then beyond it, on either side, you're going to find that this capital M is a little bigger than the y values right nearby. So the graph would do maybe this kind of thing. And in that area, in that neighborhood, that's going to be the tallest point. That's all this says right here. It says that y value is greater than or equal to the y value of the function nearby. And you might think, well, why did they say equal? Well, it does actually equal the function at that one spot, right, at itself. So that's why that equal to option had to be there. If I can just get my notes to flash back here, 1 second. There we go, everything's back again. This issue of it being the biggest y value in that area, in that neighborhood, is a key thing. It doesn't have to be the biggest value everywhere. It says for x near this place. So anywhere kind of around here, that has to be the biggest y value. But it can still be what we would call a relative maximum if the graph actually went up higher than it later. So maybe the graph looks like a crazy W shape. That's okay. As long as in that neighborhood where I've highlighted in turquoise there, that's the biggest y value. And it could happen because the graph is nice and flat. Here's another possibility. Maybe right here at some x is equal to c, we're at some big maximum value, not because the graph is flat. Maybe the graph goes up and has like a little cusp right there. That could happen too. That would also be a relative maximum because in that neighborhood, that's the biggest y value that we can see. The exact same thing happens backwards for local minimums. Right, so if we've got this, it says a local minimum value of m, right? M for minimum, m for maximum. Okay, so maybe right here, this might be my minimum value, and it occurs at some c for x, and that could be because the graph goes and kind of bottoms out, and it might actually go lower than it later. That's okay, but in that neighborhood, like right nearby, that's the lowest y value. It could be because the graph is nice and flat, like I've drawn there, or maybe it could happen because there's some sort of cusp, some sort of point of non-differentiability where the graph comes down, hits that minimum y value, and then goes up later. As long as we look at it and say, yep, in that little area, in that neighborhood, that's as low as it's going to go, then we can say that that is a relative minimum or a local minimum. So local, relative, completely interchangeable. Next issue, a little bit of vocabulary. A critical point, sometimes called critical numbers. That's a point on the function where one of two things are going to happen. I mean, basically, let me do it this way. Let me say that these places that you can see up here, these are critical points. This place here, or that place there. Also on this one, even for minimums. There and there. So what is it that's happening in terms of the calculus? What's the derivative doing there? Well, on the ones on the left in each of our boxes here, it looks like the graph is flat. The derivative would be 0. So either the f prime is going to be 0, or you could have no tangent at all because the derivative doesn't exist. So either f prime of x is equal to 0 or f prime of x does not exist. It's got to be one of those two things. We're going to use the idea of looking for critical points to try to find places where graphs might hit maximums or minimums. Now, when we do that, when we find these critical points, there's an issue where not every single critical point is going to be a maximum or a minimum. Sometimes they can be these interesting little things called inflection points, but if there's going to be a maximum or a minimum, then you're going to find it at a critical point. This is actually Fermat's theorem. Now, this is a theorem, it's not a definition, so the arrow of kind of logic only goes one way, and it says if your graph, f of x, does have a local max or a local min at some interior point. So I'm not talking about endpoints. The endpoints at the end of a graph, they can be kind of unusual. So I don't want to talk about them for a minute because you might have a graph that's going up and then stops, and it's going to have a maximum there because in that neighborhood you can't get any higher than that. But it's not gonna kind of fit with Fermat's theorem here. So that's why we say it's got to be an interior point stuck inside some valid interval. Then you're going to find that it's definitely going to happen at some sort of critical point. Either the derivative at that place is going to be 0, or it's going to be does not exist. It's going to have to be one of those two things. So in other words, it's going to be a critical point. But be careful because it doesn't work the other way around. So not all critical points are maxes or mins. Let me show you a few examples so you can see that. This first example, we're just looking at y is equal to x squared. And there is a critical point on this graph right there where the graph is flat. And so if we're going to be trying to look for maximums and minimums, it could be useful to try to find any critical points, and this one's definitely got one. So it's got a critical point right there. And then with a little analysis, which we'll start to do in this chapter, we can look and go, hey, that is a nice little local minimum. Okay, so that critical point was a max or a min. Let's try this next one out. Let's try absolute value of x. What about what's going on right here at 0, 0? That is a place where the derivative does not exist. There's no clear tangent line there. And we would say, oh, hey, look, you found a critical point. And sure enough, it's actually a nice little local minimum. So far I haven't been able to prove my story here that not every critical point is going to be a min or a max. Well, here comes one. What about y equals x cubed? Kind of looks like a little slithering snake. And if you go and do your calculus, you will find that there is a flat spot, a perfectly flat spot right there. So this is definitely a critical point. And if we're trying to find minimums or maximums, we might actually go and say, hey, we found an interesting place. At x equals 0. Looks like the graph is flat there. But that particular place, it is not a max or min. It's neither of those. All I'm saying is if there is a max or a min, it will happen at a critical point if it's an interior point on the graph. But not every critical point is going to be a max or a min. So this arrow up here for this theorem, it's kind of like saying, go and do a little biology analogy here. It's kind of like saying if it is a cat, then the logic says it is an animal. So you're wandering through nature and you pick something up and you go, what's this? And you go, oh, it's a cat. It's guaranteed to be an animal. But just because you pick up an animal, it's not guaranteed to be a cat. It might be a horse or a dog. All right, so that's going to be kind of our strategy for finding these maximums and minimums. It's going to be like, oh, you know, if you want to find cats, then let's start looking for animals. Because if there's going to be a cat, if there's going to be a max or a min, it's got to be an animal first. It's got to be a critical point first. And then once we have a chance to stare at it, we can go and see whether or not it really is a max or it really is a min. Okay, flipping over the page, we're going to switch slightly away from the idea of relative maximums or local maximums to something a little more bold, a little more aggressive. And these are global maximums or absolute maximums. And the math explanation for it says a function f of x has a global, or again, interchangeable with the word absolute, has an absolute maximum if you found a y value where that y value is as big as the function ever gets for all x in the domain, not just in some neighborhood nearby, but it's the largest value ever on the graph. Whereas before, if I can go back, we would say, oh, well, look, this is a maximum in a local sense because in that little turquoise highlighted area, that's as big as you can get. But it's not as big as the y value is here. So we're going to be going and saying, no, where is the very, very best maximum? Or where is the very worst minimum in the graph? Okay, and so the minimums are over here. An absolute minimum or global minimum is a y value where the function gets that low, and that is it. That is the smallest value ever. Right? You're never going to find a y value less than that. And it's going to actually be this y value right, if I can get my pen to go right here, that y value or that y value will be either the biggest one ever or the smallest one ever. Now I just want to play around with some functions here on different intervals to see when I can be guaranteed that I'll find some sort of global maximum. So I'm going to play around with a very easy graph, just y equals x squared, just a nice parabola, but I'm not going to graph it for the entire graph paper. This first one here, I'm going to graph it from -1 to 2, but with hard edges. And if I graph my parabola on that interval, it begins here and it finishes at 2, 4. Finishes there. Hard edges, nice filled in circles. And the graph goes like this. Okay, let's keep doing all the graphs here. The next one, we're going to go from -1 up to almost 2 for x. Well, then that won't quite hit the end. That'll look like that. The next one goes just from 0 to 2, not including the 0 and not including the 2. So that would go like that. And then this last one, okay, this one is actually going to have the entire parabola in there. So it's going to come down and go like this. And just keeps on going up to the sky up there. Okay, let's talk about absolute maximums and minimums. And just to be clear, when I say that, I'm talking about y values. What is the biggest and smallest y value you can see in that restricted domain? Well, the biggest y value I can see on this one, it occurs here, and it's a y value of 4. Definitely does have an absolute maximum. The lowest y value is there at the origin, it's 0. So that graph, it did have an absolute maximum and it did have an absolute minimum. And remember, with this example, we're trying to figure out, well, when can you be guaranteed that these maximums, these absolute maximums are going to be there? The next one, the absolute minimum, I'm going to fill that one in first, is still 0. But the absolute maximum is an interesting question. What's the highest value that this function gets to? Well, if I look at the rule up here, it says it does have to equal it, right? It does have to be that value at some point. So what is the largest y value that it ever actually does exist at being? And you might go, well, 4. Well, no, it doesn't get to 4, right? That's an open circle. And you're like, 3.9. Oh, well, doesn't it get bigger than 3.9? You're like, oh, okay, 3.99. Well, doesn't it go as high as 3.997? And what's interesting is this graph has no number that you can say, hey, look, I saw it get to that value and it never got higher than that. So this is a good old doesn't happen, does not exist. There is no absolute maximum for that graph. There's no number I can pin it down to be. And for the same reasoning, this graph does not have an absolute maximum or an absolute minimum. There is no lowest number that it gets to because it doesn't get to 0. Now the last one doesn't have an absolute maximum, but it does have an absolute minimum. It does bottom out at a y value of 0. So what's the point of this example 4 here? It's basically this. We're basically going to look at this and say, you know what? These 3 columns over here, they are a big disappointment. There is no guaranteed absolute maximum or minimum when the story looks like that. But this column over here, this is typical. You're going to find that there will be, it'll be there somewhere, some sort of absolute maximum or minimum. But what it has to require is the function needs to be looked at over some closed interval with those hard edges. And so this is actually the extreme value theorem. It's one of our theorems for the course. And it says if f of x is a nice continuous function, all of our theorems are going to require that, on a, here's the important part, closed interval, like that first column from -1 to 2, including -1 to 2, right, has to have those hard edges there. Then that function has, I'm not telling you where it is, but it's going to be there, has both a maximum value and a minimum value somewhere in the interval. It does not tell you how to go and find it. So you're on your own trying to find that absolute maximum or minimum. All we know is that they will be there. Okay. Now it's called the extreme value theorem. I'm gonna just write that in everyday common language just to make this a little bit simpler. So when they say extreme, they mean really big or really small. How about we rewrite this and we'll say, okay, instead of extreme, let's go, this is the really big. And when they say value, it's like, well, value for what? Well, it's actually y value. So this is the really big y value. And theorems are just rules. So this is the really big y value rule. Right? Let's keep it a nice simple language. It says there will be a really big, biggest possible y value somewhere in that interval, as long as the interval is closed. Okay, it's time to put what we've seen together here with one last little bit of theory. Then we're going to try this out. We're going to be using calculus and applying our calculus to try to find places on the graph where we can hit these extremes, these absolute maximums or absolute minimums. That's going to be our goal. Now, it's going to require that we've got some nice closed interval for this to be easy, because then we'll be guaranteed that those maximums and minimums are out there. And our plan is to do this. Look for all the critical points. Okay, those will be places where the derivative is either 0 or the derivative does not exist, right? So f prime is 0 or f prime does not exist. Check them out. Check out all those animals, because you might find some cats there. And then check out the endpoints of the interval. Go and check out what's happening for the function at the very beginning and the very end. We saw this up here, right? Like if you take a look, the biggest value on this first graph was actually 4, and it's not because the graph is flat. There's no critical point there. It's actually just beautifully going up and then it stops. So sometimes graphs will be climbing and climbing and climbing, and then they just have to finish, and that might be the place where you find the absolute maximum. So we do want to go and definitely check out our endpoints just to make sure that that's not where the maximums are hiding. And then you just select, you pick from all the ones you've seen, the very biggest and the very smallest y value. That'll be our plan. Now we're going to try that out over the next couple of pages. And I need to tell you that it's going to take us about 4 lessons to get to the point where we can really put everything together. So if you're looking at it and going, well, how would I know this particular issue on this question? I hear you. It's going to be a little frustrating for the first day or two. We might need to lean on our graphing calculator a little bit, but then at some point after about 4 lessons, we'll be really, really good at this. So it says find extreme values. That means really big, really small values for this function on this nice closed interval. So I'm pretty happy that it's a closed interval. That does tell me that there will for sure be an absolute max and an absolute min somewhere in there. Now, I'm not too keen on the way this function is written. I might want to make a little change here and say, hey, how about we rewrite this just as a power? This is x to the 2/3. Okay, let's go and do a derivative. The derivative for this function is going to be 2/3, that comes down, x to the -1/3. Now I am going to tidy this up a little bit. I know in the previous chapter we never bothered, but here it could be useful. This has a 2 in the top, and then there's a 3, and then a cube root of x down there in the bottom. And the reason why I want to see that derivative is I'm going to be going and looking for critical points, right? This is going to be one of my main plans, right? Look for those critical points. Looking back at this picture here, yeah, it was the critical points where we can maybe find some maximums or minimums. And those critical points are places where the derivative is zero or the derivative might be busted. So I like to always set up my work like this. I say, okay, there's the function. And then I'm kind of wondering, I'm just kind of curious, does that equal zero? Does that ever happen? Or does that equal does not exist? Could it be one of those two things? And so I start staring at this fraction. Now this fraction has a top to it, a numerator, and it's got a bottom to it, right, a denominator. If you want your fraction to be zero, it has to be the top that's equaling zero. There's no way that can happen on this one because all that we have on the top is a 2 and it's busy being 2. So that fraction can't be zero. So if I'm looking for critical points, I'd have to say, you know what, that's a never. And sure enough, take a look at the graph. It's never flat, right? This is what we're looking for. Like if the derivative is 0, it's like, where's it flat? Well, never. Okay, well, what about a derivative that's broken? Is there a way we can make this fraction broken? And the answer is sure, if you can make the bottom equal to 0. And yeah, we can pull that off if we were to make x equal to 0. You can do the cube root of 0, but you just can't divide by 0. And sure enough, looking at the graph, there's this critical point right here. So we should go and explore that point. It might be a place where there's an absolute maximum or minimum. And you may be looking at the graph going, well, of course, like look at it. I know, but this graph is here just as a courtesy. Sometimes you'll be doing this with no graph and no calculator. So you're just sitting there going, okay, what can I do just analytically by hand? We're going to check out that point, and then we're also going to check out, as much as we can, the endpoints to see what's happening there. And then we'll just pick and see which one is our very best and our very worst. Now I can see that there is a nice little local min here. In fact, there's an absolute min. There is a local max here, but it's not the absolute. And there is a local max here, and it's also the absolute. Okay, at this point, what I would do is start calculating. Just check out values at all of those interesting points. Check them out at -2. Check out the y value at 0, that critical point we had. Check out the y value at 3. I'm using the function, not the derivative, because I want to see y values. Now I'm going to save you a little time. This one ends up being 1.5874. This one's 0. This one is 2.0800. So if you were being asked, please go and find the absolute minimum and go and find the absolute maximum, we're done. We're done. This is the lowest number of the 3 that I'm seeing. So that's going to be the absolute, or sometimes called global minimum for that story. And 2.0800, that's bigger than the other numbers in this list. So that is my global or my absolute maximum. Now, this spot at -2, 1.58, as I mentioned a minute ago, it technically is a local maximum. It's just not the global maximum. And here's why we would call it a local maximum. In this neighborhood, it is as high as you can get. So that's all we do for testing the local maximums and local minimums. Is just test their neighborhood. Okay, a couple more. Let's try this one out. All right, for this one here, they didn't tell me about the domain like they did in the previous example. They just kind of left me with it. What I can see is I wouldn't want to have numbers in for x that are so big that I would have a negative under the root sign. And so up to 2 or down to -2 would be okay for the root. But if you actually put 2 or -2 in, you can root 0, that's okay, but you don't want to divide by 0. So actually the domain for this function, the allowed values for x, and we don't need the graph to see this. We could do analysis in our head to figure it out. But the domain is from -2 less than x less than 2, not including the -2 and the 2. Now if you'd rather, you can write that -2 with a soft edge and 2 with a soft edge. Okay, time to go and see if we can do a derivative here. The function, if I want to just write that in a more useful format for me, this is 4 minus x squared all to the negative 1/2. That's the function. It's got a root and it's down in the denominator. Here comes the derivative. So f prime of x, take a derivative. Okay, it looks like a power with a chain rule. So it's good that we've got all those rules from chapter 3. 4 minus x squared. Lower the exponent by 1. And then the chain rule is going to kick out the derivative of this, which would be a minus 2x. It's worth it to tidy it up. We've got some negatives that cancel and a half and a 2 that cancels. We can rewrite this. So worth cleaning it up a bit as being a fraction. And in the top, there's going to be just an x, just a plain old x. And then down in the bottom, there's this binomial that's being square rooted and cubed. And you can do that in either order. So maybe I'll square root 4 minus x squared and then cube that. Okay, I'm wondering, is that derivative ever going to give me a 0 value where the graph will be flat? I mean, I kind of can see that's going to happen right there, right? Or is it ever going to give me a does not exist where the graph could have a little cusp in it? Because those could be, well, those would be animals and those could be cats, right? Those would be critical points and they may be extremes. So could this fraction ever be 0? Could this derivative ever be does not exist? Well, I can make this fraction 0. I can make that numerator 0 if I choose x equals 0. And sure enough, that's this flat critical point right there. Okay. Could I make this fraction all busted? Is there a way to do that? Can I get 0 in the bottom? And the answer is yeah, if this root was 0, which could happen if you put like a 2 or a negative 2 in there. So I kind of want to say, oh yeah, x could be plus or minus 2. But actually, that's not even in the domain. I'm not even allowed to go quite that far back or quite that far forward. So, you know, it's an interesting observation. But I'm actually going to have to just reject that and say, no, it's not really part of the story for this graph. So I've only got one critical point. I've got one thing that I can go and look at. I could go and put 0 into my function and say, okay, hey, what is f at 0? I'm going to use that critical number, find this interesting value for y, and I get 1/2 when I try that out, just 0.5. But right now, I'm not really too sure whether that's a maximum or a minimum. Is it global? I don't know. I don't know that it's global because this is a nice open interval here. And open intervals, there is no guarantee that there is an absolute max or an absolute min just before you even look at it. Now, staring at the graph, I can see that actually that 0.5 is the absolute minimum. But right now, I'm kind of looking at it going, well, how would I do that if I didn't have the graph? And I'm not too sure right now, so we'll have to look at some more things in the next couple of lessons. But later on, we'll be able to look at it and say, hey, that's actually an absolute minimum. It's a local minimum and an absolute minimum. It's a local minimum because in this neighborhood, that's as low as you can go, and it's an absolute minimum because on the whole story, that's actually as low as you can go. But right now, I'm still kind of wondering, how would you pull that off, though? Well, later on, we'll look and say, well, look, the derivative was negative the whole time, and then it was 0, and then it was positive, and that'll convince us that it's a nice absolute minimum. But that's down the road a bit. One more page only. This one here. Beautiful little function by piece, and it's actually been drawn there. Nice little courtesy graph. And it looks like, I'm kind of hoping this is true, but it looks like it's nice and continuous. It looks like it's connected there. Let's just double check, right? Just want to make sure it is continuous. The reason why I might want to know this is my extreme value theorem, my really big y value rule, it only works for continuous functions. So I just want to see whether this thing really is continuous. So what you would do is you would check 3 things out. You would check out the limit of the function as x approaches this transition point, which is 1. And you would check it out as you approach 1 on the low side. And you'd say, okay, what is this 5 minus 2x squared doing? So we're going to have to go and look at that. Then we're going to have to go and say, well, what is the function actually doing at 1? And then we're going to go and look at things from the other side. What about the limit of f of x as x approaches 1, but from the high side? So we're checking out three things to see what they do. And if you do a limit on this one, you can do direct substitution. That one is actually 3. When x equals 1, it is 3. And as you approach this one, if you do direct substitution here, you'll see that that's a 3 as well. So this is great. Little oh happy day moment. These are all the same, right? So this thing is continuous, right? It does actually touch. Let's go and do a derivative and see what's happening with that. Okay, so I'm going to take a derivative now and see what it would be doing. So f prime of x. Well, the function arrived at us in pieces. Let's see if we can build the derivative in pieces. So I'm just going to do the derivative of 5 minus 2x squared. That would be just a nice minus 4x. And the derivative of that one would just be a plain old 1. Yeah, and sure enough, that line leaving the scene just has a slope of 1 all the time. Now, you might be tempted to do this. This is not a good idea. You might say, oh yeah, well, x is less than or equal to 1 and x is greater than 1. Don't do that, right? Or at least don't do this equal to option, because we're not sure that it will actually be okay that this derivative will have a value at 1. And you might be like, well, sure it does. Look, the function up there had the equal to option on it. Yeah, but is there really a tangent line there, right? So we should go and check a couple of things. We should go and ask ourselves, what is the slope of that parabola doing right before it finishes? We should ask ourselves, what's the limit, right, for this derivative as x approaches 1, but from that low side? What's that slope? And then, what's the slope of the line as we leave? What's the derivative doing when you look at x's that are really getting close to 1, but from the high side? And here's what you find. That parabola, I'm just going to use this minus 4x. Now I'm going to do direct substitution with the 1. That parabola is actually finishing up with a slope of negative 4 right before that transition. But the line leaves with a slope of 1. Those are not the same slope value. I mean, clearly I can see that on the graph too, right? Like, how would you draw in a tangent line? I don't know. Where does it go? It's not clear. It doesn't have a tangent line there because of that cusp. So I definitely don't want to be saying that there's an equal to option on this thing. So it looks to me like this function is not differentiable. Not at that point. Or another way to say that, f prime of x doesn't exist at x is equal to 1. Same thing. Okay, let's go and check for some critical points. And that last little comment there is going to be helpful. So I'm going to take this derivative, and I'm going to ask, okay, derivative, could you ever be interesting? Could we ever be staring at an animal? Could the derivative be 0, or could the derivative be busted? All right, so I'm looking back at this now, and I'm going, okay, are you ever 0, or are you ever busted? Well, wait a minute, I can make it 0 if I put 0 in for x right here. That would make that 0. Now double check. 0 for x, is that actually happening here? Yeah, that parabola is happening at x is equal to 0. So what I'm locating is this flat spot right here. At x is equal to 0, we're on the parabola. The slope of that thing is flat. And then let's pick up this critical point here as well, where the derivative doesn't exist. So, a couple of interesting places. We have a critical point at this place where x is equal to 0, and we have a critical point where the graph transitions from the parabola to the line. So these are my critical numbers, my critical x numbers. You should go and check what the function is doing at those places. You might find some very, very interesting things are happening here. So you go and you check out what the function is doing at 0, and you find out that its value is 5. You check out what the function is doing at 1, and you find out that the value is 3. And then you would go and ask yourself about the endpoints. Well, there are no endpoints. And then you'd ask yourself, all right, if I got any maximums or minimums. Now again, it's going to take a couple of lessons to get this totally dialed in. It is actually an open interval. The domain for this thing is actually all real numbers. So there's no guarantee that there was going to be an absolute max or an absolute minimum. And that turns out there aren't. There is a local max right there, up there at y equals 5. I actually am going to find in later lessons that I know it's a local max because the derivative was positive before it and negative later. And then there's a nice little local or relative minimum here at x equals 1. And later on in later chapters we'll say, yeah, did you see the derivative switch from negative to positive? But right now, maybe we're relying on the graph a little bit. That's okay. The fact that there are no endpoints means that the really big y value rule, okay, if I can just go back to that, back here, this extreme value theorem, it doesn't even apply because this is a nice open interval. But looking at the graph and kind of looking at where we're going to go later on, what we can do is say that this spot here with that y equals 5, that is actually a local, or if you wish, a relative maximum. And this one with the y equals 3, that's a local min. Be a little patient with yourself. It's going to take a few more lessons before we can get everything totally dialed in to the point where we could do this without using a graph. For now, the graph is just kind of nicely there as a bit of a courtesy. And that finishes up our first lesson.